Hello, my name is Eric Schmidt, and this is my synthetic biology project to create a controlled lignin degradation regulatory system for improved overall biofuel production. This system aims to improve the biofuel production process by focusing on the biomass pretreatment step, which is typically considered one of the more costly and intensive steps to creating biofuels. Lignocellulosic biomass is a renewable feedstock source that can reduce the global warming effect of fossil fuels' greenhouse gas emissions. However, the structural and chemical composition of biomass can limit its commercialization by raising the cost of fermentation and pretreatment. Many current pretreatment methods require high cost and loss of energy input. Lignin is typically considered the main obstacle in the pretreatment process due to its high structural integrity and its strong binding to the other carbohydrates of biomass, which are necessary for later biofuel production. Here you can see in this figure the basic representation of the pretreatment process in which lignin is removed from the system while cellulose and hemicellulose are restored. To help mitigate some of the drawbacks of biomass pretreatment, I've proposed a genetic regulatory system to accomplish the removal of lignin in plants. This system utilizes the toggle switch approach laid out by Dr. Collins and Dr. Gardner in the year 2000. The toggle switch will incorporate a lignin degrading enzyme, specifically lacase, from the white rot fungi Pleurotus austriatus. The toggle switch is a crucial aspect to the design of the system since it has been shown that lacase also is able to degrade cellulose and hemicellulose, although less preferentially, which are necessary components for later biofuel production. Here in Figure 2, you can see the basic mechanism of the system. Here's the full model diagram of the system displaying all relevant elements. X represents lactose, Y represents tetracycline, and Z represents the C1 protein of the lambda phage. The toggle switch system is shown at the left side of the diagram here, which utilizes the LAC-I and TEDR pathways. A negative feedback loop is denoted by the Z pathway on the DNA's transcript here. This was included as a sort of safety net to ensure the system is not producing lacase for longer than is necessary. C1 concentration would be correlated to that of lacase concentration, so that once C1 reaches its threshold and begins to repress its promoter, the concentration of lacase should be reasonably high as well. On the right side of the diagram, LCC here denotes the gene encoding for the lacase enzyme. Lacase is initially inactivated when it's produced, and is only activated in the presence of copper ions here. The system has high resolution control by incorporating these copper ions as well as fluorine ions, which are able to activate and inactivate lacase respectively, so that lactase can go on and degrade lignin. This system is meant to reside in eukaryotic plant organisms, but more specifically in and around cells responsible for the plant xylem, which is the plant tissue responsible for structural rigidity and contains the majority of lignin in the plant. Having the system occur in close proximity to lignin will reduce the effects of transportation, which are not modeled here, and will increase the overall resolution of the system. The host species was chosen as the poplar plant due to its fast growth rate, low rotational time, and high energy content. In order to model this system, several assumptions were made. The main assumptions were that it was assumed that protein repression was hill-like, and that binding to the DNA transcripts promoters functioned as an OR gate, so that whether the lambda promoter or the LAC promoter were bound, the transcript would be repressed. Also, it was assumed that mRNA dynamics were not at steady state, and that proteins bound directly to them rather than to the intermediary DNA component. To understand the system, several simulations were run. In the first simulation here, only the activating elements, IPTG and copper ions, were introduced. This was done in order to analyze the negative feedback loop dynamics. Here you can see the mRNA concentrations as well as the concentrations of encoded proteins over time. IPTG was introduced to the system at time 100, and thus you see the effect of mRNA2 turning on, causing TET and C1 proteins to be produced, while mRNA1 turns off, with LAC being inhibited. Around time 350, you can see that the negative feedback loop has kicked in, and so that the system returns to its off state, which is mRNA1 being high and LAC being high. Here you can see the concentrations of the inactive and active lacase enzymes. Out denotes the inactive state, while LCC denotes the active state. At time 100, IPTG is introduced into the system, thus out begins to be produced. At time 200, copper ions are added to the system, and thus lacase begins to be activated. Since lacase is never technically turned off, degradation of the plant components is never exactly finished. However, the cellulose concentration does reach a steady state since the lacase is degrading over time as well. It was determined that at steady state after pretreatment, the ratio of lignin to cellulose was roughly 2 × 10⁻³ while prior to pretreatment it was 1/3. In the second simulation, all regulatory elements were introduced at varying time points into the system. This was done in order to analyze the turning off of the lacase enzyme. Once again, the system behaves in a similar way to that of simulation 1, since IPTG is again added at time 100. However, now with the addition of ATC at time 250, the mRNA transcript turns off at time 250 rather than time 350. In the figure, once again, concentrations of the inactive and active lacase enzymes are shown. Now the inactive lacase is shown to turn off at roughly the time 250 with the introduction of ATC, while active lacase fully turns off shortly after with the introduction of fluorine ions at 300. Unlike in simulation 1, in this simulation we see the degradation of the plant components ends after time 300 when fluorine ions inactivate lacase. Through this simulation it was determined that at steady state after pretreatment, the ratio of lignin to cellulose was roughly 1 × 10⁻⁴, while prior to pre-treatment it was 1/3 once again. The lignin to cellulose ratio of this simulation is roughly 20 times smaller compared to simulation 1 after the pre-treatment process, which correlates to an overall higher efficiency when the inactivating components of the system are utilized. In conclusion, the proposed system degrades lignin in a controlled manner as planned and causes a lower lignin to cellulose ratio when the toggle switch mechanism is used. It was also shown that the negative feedback loop successfully accomplished its goal in turning off the mRNA transcript after an allotted time period. Future work on this system will focus on the perfecting of the constants used as well as the time constant of the negative feedback system. Additionally, in order to minimize the lignin to cellulose ratio, the time span in which the system is on could be mathematically optimized. Thank you for your time. I hope you enjoyed my presentation. Here are the references used during this presentation.